Welcome back to Frank Stajano Explains and to the Algorithms course at the University of Cambridge for another helping of dynamic programming. This is the fourth and thankfully the last example we investigate of a problem we can solve with dynamic programming, and the problem this time is hall allocation. There's a sports hall. We have one here in Cambridge. And the management of the sports hall, the story goes, wishes to allocate the hall to various sports societies to practice various things, such as a five-a-side football or badminton, or in my case, kendo, and so on. And these activities are mutually exclusive. There you can only have one activity at a time in the sports hall, and they happen for different durations and at different times in the week. And the job of the management is to schedule these various activities so as to maximize the number of societies that get a booking. So this story was actually thought of before COVID-19, and so is now a pretty unrealistic setting since we can't go into the sports hall at all. So we could abstract away from the story and give a more general mathematically flavored description where we say we have a number of intervals over the real axis, and they may or may not overlap, and we wish to select a subset of these intervals of maximum cardinality without any overlaps between the segments in our subset. So by now you should either be super bored or extremely proficient at dynamic programming. Therefore, I highly recommend that you stop the video and at least recast the problem into a recursively expressed solution which combines optimal solutions to smaller subproblems. I don't mind if you don't write a program every single time, but at least you should write the optimal solution in the form that is suitable for solution with dynamic programming. Please do that. You will understand the rest of the video 10 times better if you do that right now. Stop the video and then continue once you have your own expression for the recursive solution on a piece of paper. Okay, you're back. On with the show. This is an example that refers to something like usage of the sports hall that they built a few years ago in West Cambridge, Philippe and Fawcett Avenue. And that has a very big hall that could be used for badminton, five-side football, jumping with a trampoline, and so on and so on. And so the people who manage this sports center get lots of requests from student societies about, I would like to use this hall for this activity, and someone else would like to use it for this other activity. I would like to use it for this interval of time. And they get all these requests, so each one of these horizontal bars is a request. It's a request to use the hall for five-a-side football from this time to this time. And this is with some granularity, I don't know, half hour or whatever it is that they decide, and they have their whole day or week planned like that. And these other guys would like to use it for badminton only for this time, but these two things are incompatible because you can't have the same people practicing at the same time. However, this one and this one are compatible. You could assign them to both. This one and this one are compatible if they start. This one ends here and this one starts at the same time, that's okay. But anything that has an overlap, these two are not compatible. You can give it to this one or this one, but not both. And so the problem they want to solve is to allocate the hall in such a way that as many requests as possible are satisfied. I could certainly allocate it to 1 and 6. That'd be great. I could allocate it to 2, 7, and 9. Could I allocate it to more than 3 at the same time? I guess I could allocate to 1, 3, 7, and 9. For example, that's 4. Could I do any more than 4? And the problem is to decide what is the maximum number of activities that can be done without overlap.
and then, of course, also finding out which ones they are. Now, it's not necessarily a unique solution, so I just found that I could do 1, 3, 7, and 9, but I could also do 1, 3, 7, and 8, for example. If I do 8, I can't do 9. If I do 9, I can't do 8, but I could do either of these. I could do 1, 3, 6, and 9, for example. So it's still 4. There's several cases that give me 4, but can I do any better than 4? So by now you start thinking like a computer scientist, and so you see there are 9 possible activities, each one of which can be included or not included in our solution, and so I have a string of 9 bits which can be on or off. And so I have exponentially many configurations to examine in the number of activities. So I have 2 to the 9 ways of selecting or not selecting things. And some of them are not allowed because they contain overlaps. So the one with all 1 bits on clearly is not allowed because so many things overlap. But of the ones that don't have overlaps, like 1 and 6 on and all the others off, each one has a score that says how many activities there are in it that are allowed. And I want to select one that has the maximum score. Having ruled out doing it by brute force, I want to see if this is a problem that can be solved with dynamic programming. It looks like it might be, because besides having these exponentially many cases, I also have this optimal substructure, such as if I select a 7 to be part of my optimal solution, then the optimal solution is going to be made of 7 plus whatever the optimal solution is for the problem restricted to this part, and whatever the optimal solution is for the problem restricted to this part. So I take out any activities that overlap with 7 because they clearly couldn't be in the same solution as 7. I remove the 6. Then everything before 7, I find an optimal solution for that. And everything after 7, I find an optimal solution for that. And so within here, I find, for example, I take 2, and I say if 2 is in the optimal solution, then the optimal solution is going to be whatever is before 2 without overlapping, which is nothing, and whatever is after 2 without overlapping, which is also nothing. And so if 2 is in the optimal solution, then the optimal solution is just 2. Now, you have to remark that if that I put in front of it, because I'm saying, if 7 in the optimal solution, then the optimal solution is 7 plus the optimal solution for this plus the optimal solution for that. But nobody guaranteed that 7 was in the optimal solution. So I have to say, if it's true, then this is the answer. But the true answer, the answer to that if, is given by trying all of the activities in that section in turn and seeing which one with its own score gives me the best value. So 2 would have given me a value of 1 for this interval between 1 and 9. But if I had chosen 1, I would have got 1 and also 3, or 1 and also, no, only 3, because where was I stopping? 9. 1 and 3, or 1 and 5 would have both given me 2. So clearly, activity number 2 is not as good as activity number 1, because number 1 gives me a score of 2 instead of a score of just 1 activity. And I should try all 5 of them and see which one gives me the highest score. And then that's the one that I should combine as the best stuff I can put to the left of 7, and then the best stuff I can put to the left of 9. And that is also in the context of saying, well, 7, I had hypothesized that 7 was part of an optimal solution, but nobody told me. In fact, I should try all the others and see which one gives me the best score. So to do that in a bottom-up fashion, what I would do is, again, build a matrix. And here the matrix would have, again, it's indexed by the activities in both the columns and the rows. And each square in each cell in this matrix says, for example, this one would say that's 315. So the meaning of 315 is if I look at the range between 3 between 3 and 15, what I'm going to write in this cell is the optimal solution, the best number, the highest number of activities that don't overlap between 3 and 15. And I can't do that very easily, but it is much easier if I go from the bottom up. So first of all, I consider things on the diagonal where it's just between 1 and 1. Well, there's no possible activities because the interval has 0 length. So all these things are going to be zeros. And I fill in a diagonal of zeros. Then next, I look at the things on the next diagonal, which is this cell would be 1, 2. So 1, 2 means what's the optimal solution for the interval between 1 and 2? If there were an activity completely contained in here, I would take that, but there is none. So no activity is here. And for 2 and 3, also no activity. In fact, I look, and no activity is as short as just one slot, so there's going to be nothing that fits in with just a difference of 1. So all of these are also going to be zeros. And I go here and I make another diagonal of zeros, and my job is, sorry, wrong place. My job is easy for the moment. I keep going, blah, blah, blah. And the next one would be intervals of size 2, so 0, 3, between 0 and 3. Between 0 and 3, I have at least one, and there's other few things that have length 2, and so I can probably get some mileage here. Now, between 1 and 3, are there any activities that completely stay within 1 and 3? Well, there's only this one. And so my optimal solution, as I said earlier, was going to be the best choice between all the activities that fit in here. Well, there's only one, so this one. 1 for this, plus the best choice for the things to its left, there's none, and best thing to its right, there's none. So this is just this one. And so in this slot 1, 3, I put 1. And if I wanted later to be able to reconstruct what the optimal solution was made of, I should remember somewhere this one was made of activity 1. That's the one I chose to write this one number of activities. If I go to the next cell, which is 2, 4, then between 2 and 4, to fill in this cell, and between 2 and 4, there's nothing that is completely contained, and so this one is going to be a 0. But if I keep going, between 8 and 10, I see 1, so 8 and 10, I see 1. That would be this one. And if I, so that's from activity number 6. As I said earlier, if I wanted to remind myself how this came about, I would say I'm taking activity 6. And that will come in useful later when I reuse that to say what my optimal solution was altogether. And then I keep going. And so when I come to something less trivial than the ones I've done so far, for example, this one that I had marked in red over here, this is 3 to 15, then this means I'm looking at this range. I first of all have to look at all the activities that are completely contained between 3 and 15, so not this one, not this one's totally out. 3 is in, 5 is in, 6 is in, 7 is in, 8 is in, 9 is not in because it's partly out. And so for 3, 5, 6, 7, and 8, for each one of them, I have to compute their optimal solution. So for 3, it would be 1, counting this one, plus anything to its left, there isn't, and anything to its right. So I have to run the optimal solution of this. The optimal solution of this is from 7 to 15. So 7 to 15, I go into my table and I look up 7 to 15. That's a cell here. And this cell here, 7 to 15, is something that I will have computed earlier because I am going by diagonals like this. And so before I reach here, I will have already computed it. So I can read out a value here. And so I'm going to have some min of 1 for 3, 1 for 5, 1 for 6, 1 for 7, and 1 for 8. And the 1 for 3 is going to be nothing because there's nothing before 3, plus 1 counting 3, plus the best thing I get from here. So it's going to be 0 plus 1 plus min of 7, 15, which I can just look up. So I make this sum of things that I can read out, and I get a number. And then I make the same sum for these ones, for this one, for this one, for this one. Then I find the minimum of these numbers, and that's what I write in here. And that's how I fill in this matrix bottom up. And when I get to the last entry here in the corner, then I have the best solution between 1 and 16. All right, so that was solving this problem with the technique of dynamic programming. And stay tuned, because we will actually also solve it with a different technique later on.
Well, there we go. Thank you for watching. Special thanks to those of you who are clicking the like button and subscribing to this channel. I really appreciate it, and it means YouTube is more likely to show this material to other people who might benefit from it.